Will do.
All right, so lecture 10, method of characteristic, and we're going to work on the case of repeated roots. For the repeated root, in order to get that, so for repeated root, we have one solutions to start with. To get the second solution, because this is the second order differential equations, we need to find the second solutions based on the first solutions, and we use something called reductions of order to do so. All right. So the learning objective of this lecture is to form the characteristic polynomial equations and identify repeated roots. And we use reduction of order to find solutions of homogeneous and non-homogeneous, just homogeneous differential equations, not the non-homogeneous, sorry about that. For the case of repeated root, we're going to consider the similar or the similar equation that we see in the last lecture. This is the linear homogeneous second order differential equation with constant coefficients of the form a times y double prime plus b times y prime plus cy equal to 0. Again, where a, b, and c are arbitrary constant. Again, those depend on the problem you're working on. And from this second order differential equation, you turn into the characteristic equations, and hopefully you're familiar with this process already after taking the test. And you turn that second order differential equations to the characteristic equation of the form ar squared plus br plus c equal to 0. And you can factor this quadratic equations or use the quadratic formula to find the root of the equations. So this is the quadratic formula. And in this case, suppose you have b squared minus 4ac equal to 0. So this term is 0. And the only root that we have is negative b over 2a. Right? So this is called the repeated root. We have r equal to r1 equal to r2 equal to negative b over 2a. And from here, at least you can write down one solution, that is y1 equal to e to the rt, right? For r is equal to negative b over 2a. That's one solution, but this is the second order differential equation. Is tend to have two solutions, right? So y1 and y2. But there's no way from the look of the root that you can have the second solutions. And to find the second solution, we use the reduction of order method. Right? And I'm going to show you the procedure how to get the second solutions. And this particular method can be used to find the second solution for the linear homogeneous second order differential equation with constant coefficients. Okay. In addition to that, we will encounter a different class of differential equations. So this is the second order differential equations. It's going to be linear, it's homogeneous, but the difference is that this with non-constant coefficients. Okay, so in example 3 and 4, we will encounter that type of differential equation that we haven't seen before. Okay, so first thing first, given the linear homogeneous second order differential equation with constant coefficients, and from the repeated root, we know the first solutions. Now to find the second solutions, here's the procedure. Okay, so suppose we have one solutions of the second order differential equation of this form, a y double prime plus by prime plus cy equal to 0. To find the second solutions, we let y2 equal to v of t times e to the rt, where r is equal to negative b over 2a. Okay, so the form that we need to use is v of t times e to the rt. So here's a few things. Right? In the last lecture, you talk about, or in lecture 8, you talk about two solutions for the second order differential equations, and you need to make sure that the two solutions are linearly independent, or they form a fundamental set of solutions. And in order to show that y1 and y2 are linearly independent, then you need to check the Wronskian to be different from 0. Now, you don't know, for this case, for the case of repeated root, you know the first solution, but you don't know the second solution. So in a way, you make a trial solution. And for this trial solution, it needs to follow the category that y1 and y2 have to be linearly independent. Okay, and to avoid linearly dependent solutions, right, you need to have the multiple of the first solutions to be v of t. So some function depends on t. This cannot be a constant. You don't want a constant multiple of the first solutions. You want something different from the constant multiple solution of y1. So that's why we make a guess or the trial solutions of v of t times e to the rt, for e to the rt is the first solution. Okay. So that is the assumption, right? So we suppose we have that, going to find this form of y2, right? In the way we're going to find v of t. And again, the idea of this trial solution is that based on the first solution, let's try to use that to find the second solution. And the second solution has to be linearly independent from y1 of the first solutions. Okay. Then from here, y2 is a solution to the second order differential equation. That means you're gonna find the first derivative, the second derivative, and then substitute everything into the differential equation and find the form of v of t. Okay. Then we have that y2 prime is equal to, you take the derivative of this product right here, right? So v of t times e to the rt. So you have v prime times e to the rt plus v times the derivative of e to the rt is r times e to the rt. Okay, so that's the first derivative. The second derivative of y2 is, so a product rule here and a product rule here as well. So let me rewrite this a little bit. V prime e to the rt plus r times v times e to the rt. So product rule here, that is v double prime times e to the rt plus v prime times r times e to the rt plus r times v prime times e to the rt plus r squared times v times e to the rt. Okay. Again, the first two terms of this derivative is taken from the derivative of this product. And the last two term is from the derivative of this r times v times e to the rt. Now we're going to combine these two terms together because they are like terms. And so we have v double prime times e to the rt plus 2 times r times v prime times e to the rt plus r squared times v times e to the rt. So you have the second derivative, you have the first derivative, you have the form of y2. So we're going to substitute all of them into the differential equations. So substitute y2 prime, and y2 double prime into the differential equation. We get that. So a times y double prime, that is a times v double prime times e to the rt, plus 2r times v prime times e to the rt, plus r squared times v times e to the rt, plus b times y prime, that is plus b times v prime e to the rt, plus r times v times e to the rt, plus c times y, or c times v times e to the rt, and this is different from equal to 0. Okay, so every term in the left-hand side on the left-hand side has e to the rt as the common factor. Okay, so that is different from 0, so you can divide both sides for e to the rt to get rid of that and make the problem a little bit easier to do with. So the next step is to get rid of e to the rt. Again, e to the rt is different from 0, so you can divide it out of the equation. And you're left with a times v double prime plus 2r times v prime plus r squared times v plus b times v prime plus r times v plus c times v equal to 0. Okay. Now, this is the equations where you have the second order differential equations, and that is only depends on v. Right? It's the equation depends on v. Right, now next up, you're going to distribute and combine like terms in terms of v double prime, in terms of b prime, and in terms of v. So I distribute a, I have a times v double prime plus 2ar times v prime plus a r squared times v plus b times v prime plus br times v plus c times v equal to 0. Okay. Now I have a times v double prime plus v prime as a common factor, and I left with 2ar plus b plus v as a common factor. I left with ar squared plus br plus c equal to 0. Okay. Any questions for this step? Again, from here to here, just basically combine like terms. You only have one term related to v double prime. You have two terms related to v prime. So v prime as the common factor, and you have three terms related to v. So take out v as the common factor. Okay. Here's a few things that you have from the setup. That is, starting from the second order differential equation, you get the characteristic equation of the form AR squared plus BR plus C equal to 0. So we're going to use this expression and replace that here. Okay, so AR squared plus BR plus C is going to be equal to 0. So this term right here is 0. Okay. And now you're left with just A times V double prime plus B prime times 2AR plus B equal to 0. In addition to AR squared plus BR plus C equal to 0, you have another information here that is R is equal to negative B over 2A. Right? So that's from the first solutions. So you take out R, right? Replace that with negative B over 2A. And you get A V double prime plus V prime times 2A times negative B over 2A plus B equal to 0. And from the calculation, this term is also equal to 0. And you're left with A times V double prime equal to 0. And A is a constant, right? So you divide both sides for A and you're left with just V double prime equal to 0. And you integrate this equation. For the first integral, you get just a constant, so v prime equal to a constant. Then you take another integral, then you have v of t is of the form. Let's say k1t plus k2. Okay. Thus, the two solutions of the differential equations are, so the first equation, the first solution is y1 equal to e to the rt, and y2 is equal to k1t plus k2 times e to the rt. Again, for r is equal to negative b over 2a, where r is equal to negative b over 2a. Okay. And we can, of course, show that the two solutions are linearly independent by checking the Wronskian of y1 and y2. We can check that y1 and y2 are linearly independent by calculating the Wronskian of y1 and y2. Okay. And let me quickly do the calculations for the Wronskian here. So the Wronskian of y1 and y2 again is equal to the determinant of y1, y2, y1 prime, y2 prime. So for y1 is equal to e to the rt, y1 prime is r times e to the rt, y2 is equal to k1t plus k2 times e to the rt, and y2 prime is going to be k1 times e to the rt plus r times k1t plus k2 times e to the rt. And if you do the calculations correctly, you will arrive at the Wronskian of the form k1 times e to the 2rt, and this is different from 0, assuming that k1 is different from 0. Okay. And that's how you get the second solutions. And the second solution is linearly independent from the first solutions, even though we use the information from the first solution. Okay. That's the reductions of order. Where's the reduction of order occur? This is occur from here, right? So you start with the second order differential equations. Now you reduce that to just the 0 differential equations. Okay. Later on, when we talk about the example of the case of linear homogeneous differential equations, with non-constant coefficients, we will clearly see the reduction of order when we have to do some substitutions to reduce the second-order differential equations to the first-order differential equations to solve the problem. Okay, but for now, this is the procedure of how to get the second solutions given the first solution. Okay, and this procedure you will see again in example 3 and example 4. Okay. Now for example 1 and example 2, this is a straightforward calculations to find the general solutions of the differential equations in the case of the repeated root. Right. So given these differential equations, you turn this into the characteristic equation. Right, the characteristic equation is r squared plus 4r plus 4 equals 0. And you solve this quadratic equations, and you will see that this can be written as r plus 2 altogether square. Equal to 0, or r is equal to -2, and this is the repeated root. Okay. So one solution, at least you have one solutions. So the solutions y1 equal to e to the 2t, and y2 is equal to e. So I'm going to base the finding from here. So k1t plus k2 times e to the -2t. Okay. With the assumption, again, that is k1 has to be different from 0. So for this type of problem, you get a second-order differential equation, and the characteristic equation give you a repeated root. You don't have to follow the procedure again. Just write out the solutions of y1 and the solutions of y2. Okay, and you get to the general solutions. Later, in the case of, again, please make sure you understand the procedure here. Later, when we encounter example 3 and example 4, we have, again, linear second-order homogeneous second-order differential equations with non-constant coefficients. Then you have to write down the details of how to get the second solution. Okay. However, when you get the linear homogeneous second-order differential equation with constant coefficients, and the characteristic equations give you a repeated root, you don't have to redo the procedure. You okay with that? Okay. Any questions on that? No. Okay. Therefore, from here, the general solutions is you have y equal to c1 times e to the -2t plus c2 times k1t plus k2 times e to the -2t. And of course, you can simplify this general solutions further. So distribute C2 and K1, C2 into the parentheses. You have C1 times e to the -2t plus C2 K1 times t times e to the -2t plus C2 times K2 times e to the -2t. And then you combine like terms. I want to make a little bit more space here. So you have C1 plus C2 K2 times e to the -2t plus C2 K1 times t times e to the -2t. So why do I do that? Again, to reduce the form of the solutions. Okay. Remember, C1, C2, K1, and K2 are just some arbitrary constants. Therefore, when you get to this form, you have C1 plus C2 times K2 is going to be another arbitrary constant here. So I'm going to use capital C1, okay, or capital A1 for that matter. It doesn't matter what letter you use. Just put that in capital case. Okay, and C2 times K1, C2 is constant, K1 also a constant, so a product also going to be an arbitrary constant. Therefore, the general solution is going to be of the form A1 times e to the -2t plus capital A2 times t times e to the -2t. Hopefully you see that, how you get the general solutions. And we're going to do the same thing for example 2. Find the general solutions of differential equations y double prime minus 12y prime plus 36y equal to 0. I'm going to write down the characteristic equations. And you get r squared minus 12r plus 36 equal to 0, or you have r minus 6 squared equal to 0, or r equal to 6. Right, so this is the repeated root, and you can write down the solutions automatically here. That is y1 equal to e to the 6t, and y2 equal to k1 times t plus k2 times e to the 6t. Again, k1 has to be different from 0. So that's the solutions. Now the general solution is you have y equal to c1 times e to the 6t plus c2 times k1t plus k2 times e to the 6t. Okay. I'm going to follow the same procedure as before over here. So distribute c2. I get here c1 times e to the 6t plus c2 k1t times e to the 6t plus c2 k2 times e to the 6t. Then again, combine like terms. I get c1 plus c2 times k2 times e to the 6t plus c2 k1t times e to the 6t. And I get the form of capital A1 times e to the 6t plus a2 times t e to the 6t. Now, if you notice the two equations here, the two general equations, they look more or less the same. So the setup look more or less the same. So you have a1, a2 as the arbitrary constants. The first term is a1 times e to the rt. Right? And the second term is a2 times t times e to the rt, for r is the repeated root. Okay. And from now on, you don't, for the general solutions, again, for the case of linear homogeneous second-order differential equations with constant coefficients, you can write down the solutions and go directly to the general solutions of this form. Right? So a1 times e to the rt plus a2 times t times e to the rt. You don't have to follow this, all the calculations to arrive at the answer. You can just use the answer directly. Any questions on that? No? Okay, good. Now, as I mentioned, for example 3 and example 4, you encounter a different class of second-order differential equations. In this case, you have a linear, homogeneous second-order differential equation with non-constant coefficients. And because of that, you need to show all the work on the procedure to get the second solutions. Okay. So here's the following procedure. Given the first solutions, 1 over t for t is greater than 0, right? So that's important. Right. Consider the second solutions of the form. So the second solutions is of the form y2 equal to v of t times y1. So in this case, you have v times 1 over t. Now you need to find the form of y2. You take the first derivative, you take the second derivative, and apply everything and put everything into differential equations. So then you have y2 prime is going to be v prime times 1 over t minus v times 1 over t squared. Right. So I just apply the product rule for this product. So first, derivative of the first function multiplied with the second, plus the second function multiplied with derivative of the second functions. So derivative of 1 over t equal to negative 1 over t squared. Now for the second derivative, again, v double prime times 1 over t minus v prime times 1 over t squared. So this two term is from the derivative of the product, v prime times 1 over t. Next, I'm going to take the derivative of this product, and I get v prime times 1 over t squared, minus v times 2 over t cubed. Okay. So I put that in parentheses because there's a negative in front of it. Okay. Now distribute the negative, and I get v double prime times 1 over t minus v prime times 1 over t squared minus another v prime times 1 over t squared plus v times 2 over t cubed. Then I substitute y2 prime, and y2 double prime into the differential equations. We get that is going to be 2t squared times y double prime, which is v double prime times 1 over t. Now combine these two terms together, they are like terms. Have minus 2 v prime times 1 over t squared plus v times 2 over t cubed. So that's the first term in the differential equations. Plus 3t times y prime plus 3t times v prime times 1 over t minus v times 1 over t squared minus y, which is v times 1 over t equal to 0. Any questions for this step? No. Okay, good. So far, I set the form for y2. Find the first derivative, then the second derivative, and substitute everything into the differential equations. Now I'm going to simplify the resulting equations. I'm going to simplify these equations. So distribute 2t squared, distribute 3t. This is what I get. So 2t times v double prime minus 4 times v prime plus 4 times v times 1 over t. Okay. Now distribute 3t, and I get 3v prime minus 3v times 1 over t, and minus v times 1 over t equal to 0. So let's simplify something here. So let me write down 2t times v double prime, negative 4v prime plus 4 plus 3v prime, you get negative v prime. This is 4 minus 3 minus 1, so this term cancel out. And you're left with just this two term on the left of the equations. Okay. So now still you have the second order differential equations. This is where the reductions of order come into place. Right. So I'm going to reduce the second order differential equation down to the first order differential equations by letting u equal to v prime. Right. Let u equal to v prime, or u prime equal to v double prime. Then we arrive at this differential equation. So 2t times u prime minus u equal to 0. Again, what I did is that I let u equal to v prime, and therefore u prime equal to v double prime. Okay. Now I'm going to work with the variable u instead of variable v. We're going to make a resubstitutions later. So this is the first order differential equation. So hopefully you know how to tackle this one. Right? So turn u prime into du dt. You have 2t times du dt minus u, and this is a separable equation. We can use the separation of variable to solve the solutions. That is du dt equal to 1/2 times u over t. Okay, or you do this integral of 1 over u du equal to 1/2 times the integral of 1 over t dt. On the left hand side, you have ln of absolute value of u equal to 1/2 times ln of absolute value of t plus some constant c. And you're going to find the value of u, right? So do some work here. So ln of absolute value of u equal to ln of absolute value of t raised to the power 1/2. I use a law of this is properties of logarithms, sorry, plus c. And then you do absolute value of u equal to e to the ln of absolute value of t to the 1/2 plus c. And you have absolute value of u equal to e to the c times e to the ln of absolute value of t to the 1/2. When you break e and ln cancel out, you get just absolute value of t to the 1/2. And then you break the absolute value, and you get u equal to plus and minus e to the c times absolute value of t to the 1/2. Sorry, no more absolute value, just t to the 1/2. So c is a constant, e to the c is also a constant, and therefore plus minus e to the c is a constant. So I'm going to let u, so u is going to be capital A times t to the 1/2, where a is equal to plus and minus e to the c. All right. So remember, what the variable that you're working with is the variable v. We are getting the solutions of u, so you need to make the resubstitutions. Okay. Since u equal to v prime, we get that v prime or dv dt is equal to a times t to the 1/2. And again, this is separations of variable. You get v equal to the integral of a times t to the 1/2 dt, or this is 2/3 times a times e to the 3/2 plus some constant capital C again, or capital K, just to avoid confusions here. Okay, so that is v. And therefore, when you know v, you can arrive at the second solutions. Okay, so the second solution is, so you have y2 is equal to, let's see the form of it, y2 is equal to v times 1 over t. So for v is equal to 2/3 times a times e to the 3/2 t. Sorry. So this is the mistake here. So you have 2/3. Let me be careful here. So a times t to the 3/2 divided by 3/2 plus constant k. Divided by 3/2, that means you multiply by the reciprocal, so that's 2/3. So this should be 2/3 times a times t to the 3/2 plus a constant k times 1 over t. So that's the second solutions. And then you can check the Wronskian of the second solutions to ensure that you have you can find a fundamental set of solutions. Right? The Wronskian is going to be different from 0. So it's a little bit of work here for the case of second order linear homogeneous with non-constant coefficients to get the second solutions. Okay. So that's the procedure. And let's take a break here. When we go back, we're going to do example 4, finish up with example 4 and move on to lecture 11. Okay. I will see you in another 10 minutes. Okay. All right. So in example 4, we're going to work on the similar class of differential equations. This is again the second order linear homogeneous differential equation with non-constant coefficients. So given the first solutions, can you find the second solutions? And from that, can you make sure that you form a fundamental set of solution that is going to find the Wronskians, and the Wronskian has to be different from 0. So given y1 equal to t squared, the solutions of y2, or the second solution, is so you have y2 equal to v of t times y1. For y1 is equal to t squared, so that is v times t squared. Then you find the first derivative and second derivative and substitute into the differential equations. Then you have y2 prime equal to v prime times y1 plus v times y1 prime, or in this case, y1 is t squared, so v prime times t squared plus v times 2t. Okay. Now for the second derivative, you have y2 double prime equal to v double prime times t squared plus 2 times v prime times t. So these two terms coming from the derivative of the product v prime times t squared. Then for the second term, take the derivative of that. You have plus v 2 times v prime times t plus 2v times 1. So derivative of t is just 1 in this case. Now combine like terms, so when you combine these two terms together, this is v double prime times t squared plus 4 times v prime times t plus 2v. Now we substitute y2 prime, and y2 double prime into the differential equations. We get that t squared times y double prime, so t squared times v double prime times t squared plus 4 times v prime t plus 2v minus 4t times y prime, which is v prime times t squared plus 2v times t. Then you take plus 6 times y, or plus 6 times v times t squared equal to 0. Then you do distributions in combined like terms. You have v double prime times t to the 4th plus 4v prime times t cubed plus 2v times t squared. Then you have negative 4v prime times t cubed minus 8v times t squared plus 6v times t squared equal to 0. So do simplifications or combine like terms here. So you only have one term related to v double prime. So v double prime times t to the 4th. And you have 4v prime t cubed. This is minus 4v prime t cubed. So that is cancel out. Then you have 2vt squared, 6vt squared, and minus 8vt squared. So they are cancel out as well. And you're left with only one term here. And this is v double prime times t to the 4th. Okay. Alright, so another assumptions that we have up here is t is greater than 0. So you can divide both sides for t to the 4th, and we only have v double prime to be equal to 0. And from here, you integrate the equations to get down to just the 0 derivative. Right? So when you take the integral of these equations, then you have that v prime is equal to k1, right? And v of t is equal to k1t plus k2, where k1 and k2 are arbitrary constants, where k1 and k2 are arbitrary constant. Thus, the second solution is, so you have y2 equal to v times t squared. In this case, v is equal to k1t times plus k2. So k1t plus k2 times t squared, and that is the second solution. And to check if they form or the solution form a fundamental set of solutions, you need to calculate the Wronskians. So here's the calculation for the Wronskians. Next, we do w of y1 and y2, which is the determinant of y1, y2, y1 prime, y2 prime. For y1 is equal to t squared, and y1 prime is 2t, and y2 is equal to this function, so right here, where you can distribute t squared to get k1t cubed plus k2t squared. So y2 is k1t cubed plus k2t squared. The derivative of that is 3 times k1t squared plus 2 times k2t. I used 2 by 2 determinant formula to calculate this value. You get t squared times 3k1t squared plus 2k2 times t minus 2t times k1t cubed plus k2t squared. Distribute and again combine like terms, see what you get. So this is 3k1t to the fourth plus 2k2 times t cubed minus 2k1 t to the fourth minus 2k2t cubed. These two terms cancel out, and you're left with just k1 times t to the fourth. And because we show that k1 and k2 are arbitrary constant, and now the assumptions that we need to make here in order to have y2 and y1 and y2 form a fundamental set of solutions, that is k1 is different from 0. So this shows that y1 and y2 form a fundamental set of solutions. Okay, so that's the procedure of reduction of order to get the second solutions given the knowledge of the first solutions. And this technique is useful to get the second solutions, especially for the case of a linear homogeneous second order differential equation with constant coefficients or with non-constant coefficients. Okay. That is for the case of repeated root. We're now going to move on to lecture 11 where we're still talking about method of characteristic but for the complex roots.